Hello friends, in this video we are going to learn how to calculate the deflection in the bar, which is composed of various materials and different cross-sectional areas. So idea behind calculation of deflections at one end of the bar with respect to another is obtained by the superposition. If the bar is composed of n number of parts, and the superposition, using the superposition concept, we can actually say the deformation of the entire bar is then expressed by the formula that is delta is equal to sigma I going from 1 to n pi li ai and ei. So this was the standard equation, but only thing is the deflection of each of the bar, each of the component of the bar can be calculated separately, and it can be added finally to get the deformation of the entire bar. So let us try to solve one example of this bar. In this figure, I am showing one example where we are required to determine the deflection of the bar. Let's say this bar at the end, A, B, and T, and it is required to calculate the deflection under the external axial loads, and at different locations there are axial loads which is acting. Let's say this is location C and this is 550 kilonewton, and the distances which are given, this is 0.3 meter, this is given 0.4 meter, this is given 0.5 meter. And first component is made up of aluminum. Second component is made up of steel. And the cross-sectional area of the first part 1 and part 2, cross-sectional area of the part 1 is 0.002 meter square. Cross-sectional area of the second part will be 0.003 meters square. Now, to calculate the deflection, it is not the direct summation or anything. What we are required to understand, the force is internal force within the different parts of the bar. Okay, so here in this case, you may notice that where are the locations where the material property changes, where are the location where loading condition changes, and according to that we have to split our bar and calculate the internal axial force using the concept of free body and equilibrium of the entire bar and cut section of the bar, and then only you can calculate, add up this deflection. It is not the direct adding of the forces. It is first we have to calculate the internal force, axial force within each component of the bar, and then we can calculate the deflection of the individual component, and then you can add it. So first step is to understand how to calculate the internal force. Okay, and that you can do it from the taking the free body diagram. So in this case, though the material property is given in a different, so I cannot say that I have to calculate two different deflections for part 1 and 2. It is not so. Here in this case, we have to calculate, look at the position of the loadings. There are 3 different locations where loading is acting. That means we are required to cut the section for 3 different parts, and we have to calculate deflection due to that 3 different parts, and then later on edit. So just don't get confused with the number of parts. It is very clear that we are required to first calculate the internal force. So first let us take the free body of the internal force, how do you calculate the first part? Of course, this is a reaction. So the reactive force is not known to us. So we start from the left hand side, okay, where the information of the forces are known to us. And free body is what you can, when you cut the section, you can show whatever the force is, those are acting on that particular. Okay, so first section is cut it from here. 140 kilonewton force is acting. So internal force can be calculated for the part AB first. Now how to show this force, which is, I will call it force in the part AB, internal force. You can show it as if the force is basically the, the outward normal, that is the bar is under tension, as if like this is your cross section and you just take the outward, okay, outward force, because that will give you actually, irrespective of the position of this force, whether it is under compression or tension, that we do not bother about it. We have to cut the section and show the position of the force in the, either you can assume that the positive x-axis, or you can assume the normal to that cross section, that is the arrow coming out of that cross section and not in, right? We always consider the positive sign conventions as tension, and it will come accordingly. So idea behind, why somebody may ask you why we have not taken the reverse arrow and why we have taken only this arrow in this direction, because it's the cross sectional and coming out, the outward force, and that will also impart the tension within the bar. And we take the equilibrium of these and we can calculate part AB. The force PAB can be calculated as, it turns out to be 140 kilonewton. So basically, if this is your x-axis, positive x-axis going in this direction, something like this, you can take that way also. So you can write something like PAB minus 140 is equal to 0 and PAB is equal to 140. This is how you can show the force direction. Okay. Now second part, we have to cut the section where your loading condition changes. Here there is no point in taking section, another section here, because the situation is same. So now you can take the position, what you can do is, you can take the another section where the loading condition has to be different, right? So what is the purpose? We can simply take the second section and show whatever the force is. We have cut the section somewhere here, second section, and here there is 260 kilonewton force is acting. Here it is, of course, the 140 kilonewton. Now look at the direction, both the forces are acting in the same direction, and I can show, of course, the outward direction, sorry, the force which is acting here. You have taken the section and this force is acting in the outward direction. So here, from here, it is acting, let's say, force into part BC maybe. So total force, of course, in the part BC will be PBC, the positive, minus 140 minus 260 is equal to 0, and PBC can be given in the form of, it's 400 kilonewton. Now the third part, it will be taken, you always have to see where my loading condition changes. So here, if I take the section here, the situation is same, right? So third section, you have to choose somewhere here. where your loading condition changes. Now I will again draw the third free body diagram. I have cut the section at 3 3, so it will be something like here. You have to show the force, and also within that you have to show the another force at point C. It is, this is 260, this is 140, this is 540, 50 kilonewton. And you can show here the outward normal of the cross section in the tension position PCD. So let us say if the force, I want to evaluate the total force within that particular internal force, basically within that cross section. How much total force is acting on that cross section will be PCD. Of course, you can see here the direction is same, so PCD plus 540 and minus 140 minus 260 is equal to 0. And you can calculate PCD is equal to 140 plus 260 minus 540. So total force will be, PCD will be given by minus, you can see here minus 150 kilonewton. So not necessary every time, you get the tensile force, you sometimes get the compressive force. The effect will be under compression also. So if you want to plot the diagram, first we have to plot the internal force diagram. Just like you are plotting the bending moment shear force diagram in case of beam, in axially loaded members, you can also plot the force diagram, that is internal force, kilonewton, and this is your x-axis. And I can show first is, if this is A, this is B, then PAB you have already seen, it is positive 140 kilonewton. Then from B to C, we can show the 400. This is your point C here. And it is again constant, the 400 kilonewton positive. Now, the third portion, that is CD, you have the compressive force. So just change your sign here and show it minus 150 kilonewton. Okay, so now to calculate the deflection, we have to use a formula, and now we can, once we know the internal force in each of the part, that is part A, B, B, C and CD, and then you can actually find out the deflection for this different part. So part 1, part 2 and part 3, we calculate deflection. That will be the total deflection, which will give you the resultant effect. Total deflection will be somewhere here at part A. So I am writing delta A. It will be sigma PL by A. So let us take the separate slide where I have the P 140. I will convert it into Newton by multiplying 10 to the power 3. The first part, we are calculating the deflection due to first part. The force is 140 kilonewton. Length is given 0.5 meter. And cross-sectional area in Young's modulus, which is given, the Young's modulus, which is given as for the steel, it is given 200 gigapascal. And for aluminum, it is given 70 gigapascal. So we will write PL over AE 140 into 10 to the power cube. This is converted into Newton. Then 0.5 is length, 0.5 meter. You can see here 0.5 meter. And divide by AE. So what is the area? Area is given 0.002 meter square. So this will be 0.002 meter square. 70 into, this is gigapascal, so we have to convert it into pascal, that is Newton per meter square. So this is delta 1 from part 1. Similarly, we write the deflection due to part 2, that is 400 kilonewton for the part 2. You have to see these three parts: the internal force and deflection due to these internal forces and the individual length. Okay, the second part, you can see here the length. Between B and C, the length is already given, that is 0.3 meter. So for 400 into 10 to the power cube, that is Newton, 0.3 meter. And you can see here the cross sectional area, that it's 0.003, 200 gigapascal into, we have to convert into Pascal, this is 10 to the power 9. Okay, this is from the second part. Third part, of course, we had the compressive force, so minus 150 times 10 to the power cube. What is the length? You can see here the length 0.4 meter, and then divide by 0.003 is the cross sectional area, and the Young's modulus, that remains same. So altogether you are getting here, if you simplify, and you can, so this is due to the delta 2 due to force in part BC, and this is delta 3 due to force into part CD. So please understand, though there are two step bars, bar is composed of two different parts, aluminum and steel, but because of the loading conditions, we have to take the three different parts and we have to split the bar in calculating our deflections. So this is very, very important. So if you simplify, you get 0.5 here. From here you get 0.2, and from here you get minus 0.1, and this is whole thing in meter. So if you want to convert into the millimeter, you can multiply that 10 to the power minus 3. Sorry, the whole thing is in, you will get here in meter, you can convert that into the millimeter. So divide by 1000, you get 0.6 mm. So if you at all want to plot the deflection of the various part within the various part, then also you can imagine the deflection. So first part, the total deflection you can see here, in from here to here is a total deflections. So I told you delta A is 0.6. So this 0.6 will remain constant up to the level B, that is location B. And then at location B, what is the deflection, that is total is this. At location B, you have this total deflection. So total deflection at location B will be 0.1. That will continue up to location C. So this will be 0.1. And the last, you can see here, minus 0.1 will be the deflection of the last section, that is CD. So you can just take the negative sign here and minus 0.1 here. So this will be 0.6, 0.1, and this is how you can visualize the total deflection is 0.6. And if you want to take the deflection in the second part, you have to take the summation of the second and the third part, and then the last part. So this is how the deflection. So you can see here the part AB and BC will be under tension, because you can see the positive deflection, and part C and D, the part between C and D will be under compression. So basically negative sign of the deflection says that bar will be shortened in that part, whereas in this first part bar will be elongated. Okay, and in the last part it will be shortened. So this is how you have to visualize the deflection diagram and the force diagram. Thank you.